Good morning, good afternoon, good evening, good wherever you are, and welcome again to another SNIA presentation, this from the Networking Storage Forum. And today we're going to be talking about securing data in transit. I'll be giving you links at the end of the presentation to talk about the others in this series, the other presentations that we've given, but today is about securing data in transit. Just a quick few words about the interface. You'll notice you have in front of you a fairly small letterbox-sized picture of the screen. You can, in fact, expand that to full size should you need to. There's a button on the right-hand bottom that allows you to do that, and that will allow you to see any detail that you might otherwise miss on the slides. The other two things that I want to point out are, first of all, before you leave the presentation today, there's a feedback button. Somebody has already, believe it or not, kindly given us a feedback, which is quite unusual, having not started the presentation to get such a positive rating. However, you can give us feedback on the presentation as you're leaving it, and any comments that you make, we'd love to hear from you. We really like to know whether we're doing the right thing here with these presentations and what we can do to improve in future. And the other thing that you might want to be able to do is pick up a copy of the presentation. You'll be able to see exactly what we're presenting today. There's a PDF file that we'll leave for your use. And last but not least, you get to ask questions. Should you want to ask a question, please do so. And if we have time available, and if the question is appropriate, we'll make sure to answer it during the presentation. Otherwise, we'll answer the questions in a separate blog, the link of which I'll point you to at the end of this presentation. So without further ado, I'd like to introduce today's presenters. My name is Alex McDonald. I'm the moderator for today, and I'm an independent consultant at the moment and Vice Chair of the SNIA-NSF. I'd like to introduce our speakers in speaking order from left to right. First of all, we have Claudio DeSanti from Dell Technologies. Good afternoon, I think it is, Claudio.
Morning here.
Oh, good morning. Goodness, we really are an international presenting team. Fantastic. Second along, we have Ariel Kit, who's from NVIDIA. Hi, Ariel. How are you?
Hi, doing great today. Happy to be here.
Good. Third along, we've got Cesar Obediente from Cisco. Hello, Cesar.
Hey, good afternoon, Alex. Thanks for having me. Looking forward to this conversation.
And last but not least, we have Brandon Hoff from Broadcom. Hi, Brandon.
Hey, Alex. How are you doing?
I'm very well. And that's a good sound check for us. We know that you're all here and ready to present, which is always good, especially when we have that number of presenters. So just very quickly before we start, a little about SNIA. We are the Storage Networking Industry Association, obviously. We're an industry-leading organization with 185 member companies supporting our activities and work. We have about 2,000 active contributing members in a multiplicity of groups and about 50,000 end users and storage pros worldwide that follow us. And we send out invitations to these kind of presentations to them, which is why you're here today. You can learn more about SNIA at SNIA.org, and in particular, SNIA.org/technical gives you a flavor and overview of the technical programs that SNIA do on behalf of the storage networking industry. The Ethernet Storage Forum covers specific topics. I'm not going to go through all of them, but you can read the list yourself. But one of the things that we pride ourselves on here is the ability to pull in industry experts to talk about each of these topic areas. And today we've got a fantastic set, as I already demonstrated, we've got a fantastic set of speakers who are going to take us through some of these pretty specialized areas that we deal with on a day-to-day basis. Last but not least, a little legal notice. Basically, this says two things. First of all, this is a copyright work, so SNIA owns the copyright on it. And please, we would be delighted if you would agree and use these materials based on our licensing here. And the second is there's no warranty with this. If any information you use from this presentation happens to break whatever you're playing with into two parts, both of the broken parts, I'm afraid, are yours. They're not our responsibility. So use this at your own risk. So today's agenda, we're going to be covering quite wide-ranging topic, but remember, this is about security in transit. we're going to be covering storage networks, a security framework describing the overall security environment. We're going to be talking about data in motion security. We're going to take a look at private and public cloud security as well, and also securing more traditionally perhaps data in the data center. But overall, today's topic is about securing data in motion. And without further ado, I'd like to hand over to Claudio DeSanti, who's going to take us through the storage networks security framework. Claudio.
Okay, thank you. So let's move on. Here we see, okay, this is a very simple example of a storage area network. And although the graphics on this diagram may seem a little dated, and what is here might be not fully representative of what you can think it is in your storage area network, think to this on an abstract diagram. No matter which technology you are using, whenever we are talking of storage networking, we are talking of, okay, somewhere there are servers that are performing compute operations and running workloads that need to access storage, which is physically located somewhere else. And there is a network in the middle that can be a Fibre channel fabric, or can be an Ethernet network running iSCSI, or there can be NVMe running on top of a Rocky network, or this could be a cloud that is accessing cloud storage. Doesn't matter what is there. This is a representation of a storage area network. You have your servers running workloads that need to access storage somewhere else. And so you have fundamental problems of, the red server has to access the red storage, the blue server is the blue storage, and the green server has the blue storage. And somewhere you have your management console that basically allows you to say, this is what has to happen, and this is what doesn't have to happen. So this is the fundamental framework that then can be morphed in different ways depending on the technology you are using to create your storage area network. So let's look at what are the security threats that this situation, that this environment can encounter. First of all, you will find, there could be attacks to the management and system integrity of your console. That's a big deal because that is your point of control. If an attack appears there, we will have some trouble. Or we can have some form of uncontrolled storage access. As we said, the red server is associated with the red storage. What if the red server is accessing the blue storage instead? It's not something that you would like to do. Maybe it's not a good idea if the engineering department is running with your financial information or something like that. And it could be even worse than that. Or you can have an impersonation, spoofing. So the green server can declare to the storage system, I am the blue server, give me access to the blue storage. And that is another fundamental security threat we have to look at. Or we can have this character that is able to access the network. And so it can see all the traffic that is going on, so can see all the communication and get information, eavesdrop information from there, or can even inject or modify the traffic. That is one of the most relevant places where data in transit has a requirement for security. Or finally, there could be some sort of physical access to the storage system that basically means, we have a media test for some other items, and the data that is kept is compromised and taken away. So these are the fundamental security threats we have to handle. Let's look at how these can be mitigated. First of all, begin with security threat 0. And again, why 0 and not 1? Because if you don't secure your control system, you are in big trouble. So the way in which we can secure the control system, your console, would be basically management security on the console, so authentication, authorization, logging, anomaly detection, or secure channels to connect to your control channels. System integrity is another fundamental piece in which, you need hardware, software, or firmware integrity, and preferably this should be anchored to a hardware root of trust. Let's look at some the other access, uncontrolled storage access. The red server is trying to access the blue storage. The way in which that is done, we have a filter that can happen at the storage level or at the network level, in which basically we define access control. And they say, no, only blue can access blue, red cannot access blue. And so Fibre channel tuning is an example of access control that can be used here, SCSI masking or NVMe namespace mapping, depending on the technology your storage is using. You have multiple ways in which you can try to implement access control rules on your storage network. The fundamental problem of this, it does not prevent impersonation. The green server can still lie and say, I am the blue server, please give me access to the blue storage, and that will happen. To deal with impersonation, security threat 2, we need another tool. We need authentication. We need basically to provide each server with a proof of identity. So something similar to your passport when someone has to verify your identity, or your driver license, something that verifies your identity, so that it's possible to verify, oh, I have the proper credentials, and so the blue has the proper credentials, can go through, green does not have it, and so it's blocked. This is the concept of authentication that is needed. Finally, we have the communication access, the fact that, okay, someone can be able to access the communication channel, eavesdrop and look at all that is passing over there, or even inject or modify what the traffic that is happening over there. So here is where we need secure channels, the way to provide per each packet or per each frame that is transmitted between the two endpoints, verify that the packet has not been altered in transit. So we need some form of cryptographic integrity that is usually done using some specific keys to compute a cryptographic check that is added to each packet in order to be sure that the information is not altered in transit. And then if you want to keep the confidentiality of your information, then you need also some form of encryption or other techniques to keep the information confidential, so that this character in the diagram is not able to see and read the traffic that is going on. Finally, when we are looking at the security threat 4 on the stored data, which basically physical external access to the storage device, that is something that may or may not happen depending on your environment, but is something that needs to be taken care of. The way in which these can be treated, the fundamental way is store data encryption, so encryption of data at rest. And the encryption of data can happen at the storage level, and then we have a self-encrypting device, or can be happening also at the application level, at the server level, or at the virtual machine SOS level, or at the hypervisor level. There are multiple places in which you can have basically higher layer encryption techniques to basically keep the data confidential and secure. So, review what we have. We say management and system integrity of your access console, of your storage console, is a fundamental technique you need to apply to maintain the security of your overall storage network. Storage access control techniques are fundamental to prevent accessing the wrong storage. They needed to be coupled with authentication techniques, so proof of identity to avoid liars to be able to access what they should not access. And in order to be sure that there is no access of what is in transit, you need confidentiality and cryptographic integrity that are provided by various secure channel techniques. And in terms of the actual stored data, encryption of data at rest is a technique that will give you a peace of mind. when we look now, okay, what do we have when we are looking at different technologies, different protocols? What do we have in terms of these fundamental techniques, access control, authentication, or secure channels? Here I just put the Fibre channel iSCSI and the NVMe over Fabrics, assuming IP over the fabrics that NVMe will run on. You can complete this table with the technology or the protocol of your choice. But when you are looking at access control, Fibre channel has a zoning or LAN masking on the array side. Many people think zoning to be a security technique. Well, it is very important to put it in context. Zoning provides you access control, does not provide you authentication, does not provide you a secure channel. So if you believe your fabric is kind of secure because totally isolated and every endpoint is behaving right, zoning can be enough to prevent unauthorized access. However, in the moment in which these new assumptions are not correct, so your fabric is not totally isolated, or you have some bad players that are connected to your fabric, zoning is not anymore enough. And for real security, okay, you need authentication, or you need the implementation of a secure channel. So the channel in terms of authentication defined in a standard, so let's see SPT, we will describe later, DHAP, FCAP, FCPAP, and PSEAP. They are all different authentication protocols based on different credentials, different documents. Someone use a passport, someone use a driver license, someone use your Costco card, or whatever you want in order to verify your identity. But that's the part of an authentication protocol. And in terms of secure channel, Fibre channel provides the ESP header, which is a way to provide encryption and integrity protection for each Fibre channel frame. iSCSI is based on IP, so in terms of access control, use network reachability techniques, so basically ACLs, which is the equivalent of zoning on the IP realm, or LAN masking again into the arrays. The fact that inside any storage array, you can decide, oh, this subset of the storage is for host A, this subset of the storage is for host B. And so, in terms of authentication protocols, iSCSI defines CHAP and SRP, but as in Fibre channel, the only one that has been really implemented and used in practice is CHAP. And in Fibre channel, the only one, again, that has been implemented using in practice among all of them is really DHAP, nothing else. And in terms of secure channel, iSCSI supports IPSec, and there will be more discussion on that later in this session. And finally, when we look at NVMe over Fabrics, okay, network reachability and namespace mapping are the names in that realm of the techniques we already described for both Fibre channel and iSCSI. As authentication protocol, there is only one protocol which is defined for NVMe over Fabrics, is DHCHAP, basically a CHAP protocol on steroids, extremely much more enhanced to be able to cover many more security corner cases. And in terms of secure channels, TLS is what NVMe over Fabrics define to get these. User TLS 1.2 is defined, and 1.3 is now in progress, will be defined within a couple of months. And with this, I'm basically done with my part. Be ready, because this last part is what the following part of this presentation will focus on, the secure channel.
Thank you, Claudio. Apologies, by the way, to the audience if the audio was a little crackly there. But thank you, Claudio, for that overview of the security environment that we're working in. So, again, without further ado, I'm going to hand over to Ariel from NVIDIA, who's going to take us through data in motion security. Ariel.
Thanks, Alex. So let's talk about data in transit, data in motion, data in flight, all defining the same. The definition of cybersecurity is the protection of internet-connected systems. This includes hardware, software, and data, and the protection is from malicious attacks such as the ones described by Claudio. In a computing context, security includes cybersecurity and physical security. Both are used by the enterprises to protect against unauthorized access to data centers and other computing systems such as edge computing. I always like the layers approach, as in the OSI model, which I've used in the diagram, and I look at security in the same way. Everyone needs security, and we need security in every layer. First of all, we need, if you look at the left side, root of trust, which cover the authenticity and validity of the system and software. Because if you can't trust the system, how can you trust the protocols and the applied security? So this is basic. Once we have that, we start with secure cables at layer 1, up to the encryption of storage data and different security agents such as denial of service protection running at the application layer 7. As we need to protect the data in motion between different systems, you can see here that the security protocols are applied at different layers. When looking at network in layer 3 with IP communication, IP security can be applied such that all the payload of the packet coming after the IP header is encrypted and verified. This is happening at the infrastructure level, while in the case of transport layer security, TLS, this is happening at the higher level in which there is a TCP connection between different applications, and encryption is handled per connection, encrypting all of the payload, and eventually this is an encryption in the context of the application. The security can be applied on different levels, such as that infrastructure provider, for example, can encrypt all of the outgoing traffic using IPSec, while each application running on the data center or workload is using TLS for privacy. So as this is a layered approach, the visibility to the traffic really depends on your location. For where are you looking into the system? For an outside eavesdropper, he'll probably only see encrypted IP packets because this is what we are encrypting. The Internet Protocol Security, eventually IPSec, is a secure network protocol, an open standard that authenticates and encrypts the packets of data to provide a confidential communication between two computers over the IP network. This is the data in motion. IPSec includes protocols for establishing mutual authentication between agents at the beginning of a session and negotiation of cryptographic keys, these are the session keys, to use during the session. IPSec is consisted from two main protocols. Authentication headers that provide connectionless data integrity for IP packets, which also provides protection against replay or kind of attacks that play back previous packets. The authentication header main job is to protect the entire packet, excluding things that can change during transit, of course, which cannot be, I would say, authenticated. The data integrity is ensured by using message digest, while the data origin authentication is ensured by using a shared secret key to create the message digest. In order to protect against a replay attack, we are using a sequence number field in the header. Now, the other, I would say, more popular way of doing IPSec and the more popular protocol is the ESP, the Encapsulating Security Payloads, which provides confidentiality together with data integrity, data origin authentication, and anti-replay. And I think this is kind of covering all of the aspects. And this is important because ESP can be used with confidentiality only, authentication only, just authenticating the IP packet, the headers and the payload, or both confidentiality to keep the privacy and authentication. Now, some of you might ask, so is there a reason to use authentication headers today? And I would say probably not. It's more often from historic reasons. The idea was we want to protect IP packets, but we cannot use cryptography. Usually, in most of the cases, it was because of stricter export license or regulation that forbid the use of cryptography. So in these cases, you can still protect the validity, you can protect against attackers, but you cannot maintain the privacy. Now, there are two modes of operation in the IPSec. One is the tunnel mode, in which eventually we create an IPSec tunnel. This is usually used for site-to-site or VPNs, in which there is also security gateway that is usually involved, because once the packet leaves, the IPSec eventually leaves the system and then being encrypted, the IP header is being changed, so in order to eventually create a tunnel between the two entities. Now, the other mode of work is transport. In transport, we are usually using that for, as you can see in the left picture, for computer-to-computer communication. This is eventually end-to-end communication and very popular today in the data centers for the east-west communication, and eventually I would say everything done on the OS level, for example, like server-level encryption implemented in the kernel. Now, it's important to understand that once we use in the data center IPSec, in many cases today, we will use it on top of some overlay. So we have an overlay network, such as, for example, a VXLAN, orchestrated through a software-defined networking, and the IPSec will be implemented as part of it in order to encrypt that overlay. And this is done in the transport case. Now, an interesting example is IPv6, in which originally in the RFC, there was a definition that IPSec is must. But then a few years later, eventually due to pressure of the vendors, it became obsolete. And the reason for that is complexity, which I will refer to later on, which eventually caused that RFC to change. And today, IPSec is recommended as a should versus must at the beginning. And this is interesting, kind of looking at the history of kind of wanting to encrypt everything versus the actual day-to-day life in which a lot of the traffic is actually not protected or encrypted. Transport layer security, or TLS, is, by the way, it replaces the deprecated predecessor, which is SSL. So if someone is kind of telling you, I'm talking with you about SSL, SSL is not really relevant. So TLS is a crypto protocol designed to provide communication security over networks, and is the main security protocol today for the daily applications that we are all using, right? Web browsers with HTTPS, emails. In Gmail, we're always kind of the need to configure the TLS, right? The TLS ports, etc. Messaging applications, and of course, voice over IP communication. TLS is implemented on top of the TCP protocol to encrypt all of the protocol-related data, such that if we look at HTTPS, is the secured variation of HTTP. Usually websites and content providers use TLS to secure all communication between the servers and the web browsers. For example, Netflix used TLS for their streaming. The TLS protocol provides confidentiality and data integrity between the entities. Mainly, it will be used by client communicating with a server. Now, the connection is secured because symmetric cryptography is being used to encrypt the packets. In order to create a secure communication, the session keys are generated uniquely for each connection. As I mentioned, it's a connection-based security. They are based on a shared secret that was negotiated as part of the TLS handshake at the beginning of the session. The handshake itself, the protocol, is based on public key cryptography, which protects from man-in-the-middle attacks, as Claudio have shown, or the option to eavesdrop. In fact, the identity of the parties can be authenticated using the public key cryptography and certificates, which is how most of the web servers work today. In the diagram below, showing the protocol support in popular sites, it's clear that SSL is becoming obsolete, while TLS version 1 and version 1.1 are supported. However, it's clear that version 1.2 is the most common version to date and is widely deployed. More and more organizations start to require the support of TLS 1.3, version 1.3, which bring better performance and more security. For example, in TLS version 1.3, the deprecated crypto algorithms such as AES-CBC were removed. We can see today that TLS becomes also very relevant to protection of cloud-native applications. In these cases, Kubernetes expects that all API communication in the cluster is encrypted by default with TLS. Same applies to storage systems in which TLS protects the data in motion between the storage server and the client. So many people ask eventually, okay, what to choose, IPSec or TLS? So it really depends who are you and what are you doing. If it's a Web 2.0 content, application-based, software as a service, TLS is more popular and is done at the application level to protect eventually the content. So TLS will be widely used, as I've mentioned in the different examples of web, emails, etc. If you're an infrastructure or a cloud provider and you're providing the infrastructure, there's a good chance that IPSec will be used because IPSec can create a protection of communication between servers to create clusters that are encrypted. And eventually, it's of course important to also protect the side-to-side, the north-south channels. And another thing to remember regarding IPSec, it's mainly application unaware. It's not done in the context of application, it is done in the context of the infrastructure. Actually, you could even say that in many cases, there are dedicated appliances or gateways that create the encrypt all of the fabric going out or in using IPSec while there is no context of application. Now, for east-west encryption, which is not widely used today in many data centers, you do not encrypt anything once you go into the data center. In these cases, IPSec and TLS are relevant. So the decision by the different data center owners, private cloud, hybrid cloud, etc., what to use is really depends on the deployment, their preferences in security, and any existing solutions they have. TLS, for example, is widely used for a service mesh for the cloud native. Now, if you want to do RoCE encryption, for example, in a native way, the only way to do that is with IPSec, as this can be fully implemented in the hardware as part of the protocol, and it's not application aware. And this is, by the way, an interesting way to encrypt RoCE, which in many cases today kind of not the traffic itself. I would say the fabric is not encrypted. Now, another advantage for using IPSec is the case of, I would say, legacy systems or bare metal systems. In these cases, you want to add encryption, but you can't do this on the software level, or you cannot actually do any intervention on the OS level. In this cases, IPSec can be used in the infrastructure level in order to do the encryption of all of the data and protect the cluster or communication between systems without doing any change to the system itself, without the need to install anything on the system itself. So to summarize, IPSec is used for applications that don't natively support any kind of protection, while TLS is used when the application is aware to the type of protection, and usually when there is a need to protect different connection, different types of communication or API communication. But data confidentiality also comes with a performance challenge. Let's take the example as shown here in the diagram of two workloads communicating through software-based encryption. We've implemented, for example, IPSec in the OS, and now everything going out of the servers is encrypted between the two systems. The challenge here is that crypto is complex, and this kind of gets me back to the example of IPv6. It's heavy, it's compute hungry to implement that in software, or you need a dedicated appliance. But there is another challenge. Once you encrypt all of the data, then you encrypt the headers and you blind the network devices. A lot of vendors today talk about accelerating the communication, accelerating the data centers, but once you do encryption in software or with dedicated appliance, you actually blind. And then all the NIC hardware accelerators become useless. And in many cases, different people try to kind of find creative ways to try and figure out what's going on in the traffic, how to accelerate it, how to secure it. This, of course, also impacts the implementation of firewalls and other security services. So with these challenges, let's move on, and I'll hand it back to Alex for the rest of the session.
Thank you, Ariel. That's very handy. Oh, I'll just go back one very quickly. Oh dear, we're jumping back and forth. Just while we're actually on your slides, there was a question from the audience, which I think is an excellent question. What are north-south and east-west channels? You mentioned them in your slide previously. Yeah. So kind of make it as a simple north-south communication is usually between a data center to another data center, or even from the data center to the edges. By the way, everyone are today, right? All of us are probably in the edge and communicating to the data center through a north and south communication. East-west is the communication inside the data center, between the servers,
between servers to the storage clusters. All of that communication is considered east-west, and the difference is that east-west communication today is kind of inside the perimeter, and in many cases is not protected. And one of the changes that is happening now is that there's an understanding that with multi-tenancy in the data center, regulation that is becoming stricter, you need to also protect the data inside your data center, especially as many start to deploy data centers everywhere, right? We have the global data center, the edge data center, so protection of the traffic and the storage, of course, traffic in those data centers is important, and then you apply encryption in the east-west inside the data center.
Okay, thank you. That's a good description. I've just put a link up as well. I realized the link wasn't in the presentation materials at the back end. There's a link there up in that the audience should be able to see, clickable. It's the current standards for the SNIA work on the TLS specification for storage systems, which people might find of interest if they're looking at TLS. SNIA actually has some point papers and positions on that. So without further ado, let's hand over now to Cesar of Obediente to talk about private and public cloud. Cesar.
Thank you, Alex, and I appreciate it. Thanks. And this is a continuation of what Ariel was talking about. Now we see customers and organizations where they have to have, what are we going to do around encryption to protect our data centers within the data center, but also outside the data center. We all understand that a lot of our customers are now moving to a private, they have some private to public cloud strategy, as we call it, a hybrid cloud. But the question, I'm going to take you to this journey where I'm going to take you exactly what Ariel finished up with. We're going to start how we build a private data center to have integrity and encryption methodologies to protect your data when you need to have that extra layer of security. And then I'm going to end up how you're going to have that communication through the public cloud. So if we start with Ariel covered fantastic and Claudio before me, what's the reason why we want to do encryption? But the question becomes, Ariel mentioned before, is, encryption has become very heavy and very difficult and complex to do. And the reason is, the way I looked at it is three reasons. The bandwidth and applications are requirements are outpacing the IP encryption capabilities. So what does that mean? The application, which is the root elementary functionality of every organization, is the most important thing, are requiring some type of encryption. The other thing that is coming in is the link speed is outpacing IP encryption. Therefore, today we're seeing 100 gigs, 400 gigs, et cetera, et cetera. So the question became is how can we do, from an application point of view that is not capable of doing encryption end-to-end, from host to host, what can we do in the middle? And this is when we introduced what we call MACsec, or 802.1ae. And this is a layer 2 protocol, which is a hub-by-hub encryption and integrity based on data standard, with the intent to provide confidentiality, which is, pretty much allows you to pretty much encrypt the packet on a point-to-point layer 2, links. So what does it mean? If you have a router or switch and you have a device that is not, is not capable of doing encryption, you will be, and you have the capability on providing devices. What does that mean? Now you will see the packets coming in the clear from the network, from this, from the storage devices, from the servers. Then the network devices will be able to encrypt, and then send it out once it reaches the, the devices, and then unencrypt it, and then send it back again on the clear. So if you think about it, anything that happens within the data center, as Ariel was talking about, will be encrypted on a hop-by-hop basis. So the network device will, will see on the clear and then send it out and encrypt it, and then we'll decrypt it. What is important here is now that the network will allow to continue and perform all the packets that is required as seamless as it can be. Now, what is important with this is now this type of technology, which is MACsec, right? A lot of customers are using it in order because it can coexist with IPSec technologies, SSL, and TLS, as Ariel was talking about it. So this adds another layer of security in case if customers cannot apply security in the endpoints. Now, if you think about it now, we have taken it to a mesh layer because the customers can benefit from a multiple point of ways, right? Now, by doing this, we're going to protect against the middleman attacks. because anything that is occurred within the data center, in your four walls, now you're going to be able to have encrypted. So what Ariel was talking about, the east-west traffic, now we're going to be able to protect that integrity. Number two is now we can extend that to have devices that it can connect, those endpoints connect to network devices, and then can actually add support to that security. How we do that? We do that based on a protocol called 802.1x, 2010 MKA, or MACsec key agreement, which now it provides you that communication in order to have an endpoint have encrypted to a network devices. And then the most important thing is now you can do hop-by-hop encryption in your data center. Now, it's not just the data center that you can do this, but a lot of our customers are also using MACsec to connect to different cloud providers or different, WAN links. So, for example, one data center can connect to another data center. I can provide MACsec security. So if you think about it, if you go back to what Ariel talked about it and the OSI model, this is kind of covers the layer 2, your layer 2 OSI layer, right? If we move up, right, as Ariel mentioned, with a lot of technology, what we call about overlay, right? And by now, I'm sure everybody in the call should be aware that the de facto overlay technology has become VXLAN, right? VXLAN is an overlay that allows you to have flexibility, mobility, and have, from within the data center to provide, mobility from your workloads. But what happened, if you think about it, what happened when you have multiple data centers? This is where it becomes VXLAN, what we call a multi-site or multi-data centers, right? Which provides a scalable interconnectivity solution among the data center networks. Now, the question becomes is how can I provide some type of security? Because you can see in the previous slide, MACsec is a point-to-point technology. Well, with CloudSec encryption, now I can provide what, literally I can say is a multi-hop, MACsec. So what it can do is I can provide a secure tunnel between my two data centers in order to provide that encryption between the two VXLAN fabrics. I would say a lot of our customers are doing VXLAN, and this is a technology that's very used. Now, what is important here is the cloud security key change can have multiple pre-shared keys, which each can be configured with a key ID. This becomes pretty important because the pre-shared keys now are with a key and derived for key-specific traffic with integrity validation. Now, all this comes automated in a sense that we can have a controller, and now as a SDN controller, as Ariel was talking about it, and it gets deployed via, the cloud security gets deployed via BGP to exchange the key. Now, if you think about it, now I provide you a very quick set on how we're going to do it within the four walls, right, within your data center. You can provide that information or that integrity or that encryption security to say, within hub by hub, I can do MACsec. Now, if I do multi-data center or multi-clouds, I can do what we call cloud security, right? Sorry, I don't know. It's on background noise.
That's okay. It's a time of COVID. Families are important. Don't worry.
All right. I don't know. It's somebody else. It's not me. It's somebody else.
Okay.
Yeah, somebody probably has to mute. But I apologize. It's not me. So if you look at it, the third category that we want to look into is now we did a point-to-point, and we did now, multi-site, right? So if you think about it, that's the east to west traffic that Ariel was talking about it, right? So now I'm protected, within my four walls, east-west, and I can even say north-south, right? Because I can go to different data centers or anything like that. But what about now? What is this motion where now we can say, hey, I need to go and have connectivity to a multi-cloud environment. What does that mean? I need to connect mine because my organization has some type of hybrid strategy where I need to connect to any of the cloud providers, such as, let's assume AWS, GCP, or Azure, or Alibaba, anywhere. The question becomes, how can I now protect my data, which is now it's going to be transported or be, using the Ethernet as a transfer. Or even if you have direct connect, in the case of AWS, the question now, the best way to do it is doing a site-to-site IPSec VPN. With the intent now that I can create and maintain a permanent encryption connection between the sites in order to exchange information or change data between my applications that are on-premise versus my applications that are in public. So for example, I can have my web server be in the cloud and my, database or my storage be on-prem. Now I can have encryption, and I can create an IPsec tunnel via virtual routers on the public cloud in order to provide this. And if you remember what Ariel talked about, this is kind of like put everything in perspective on how we're going to implement some type of encryption model for this type of networks today. The same concept applies that Ariel talked about it. Which obviously the protocols are going to be AH or ESP, but we mainly for this type of use case we use IPsec tunnel with tunnel mode, which is pretty much the entire packet or the original packet, it gets protected by IPsec, right? The IPsec header, what we talked about it, is inserted between the IP header and the upper layer protocol. And this is very important because now I can have that connectivity between any cloud provider or any customer or any user to any type of storage device, any application across the entire, world. So those are the three examples, that we want to, showcase to you in order to you understand. So you want to be able to protect east-west traffic, and we give you some methodologies as a, MACsec and cloud security. And then from a from a cloud point of view, the easiest way to do it is create a site-to-site IPSec VPN. With that, let me hand it back to you, to Alex.
Thank you very much, Ariel. Thank you. Apologies for the small child in the background of the whoever was on the call there. I find it quite entertaining that we all have to, live with working at home and et cetera, et cetera. And it's sometimes a good reminder that families are really important to us. I answered one of the questions by putting a link, by the way, in the announcement for what is BGP. It's Border Gateway Patrol, and there's a fairly good description on Wikipedia. I'll leave it up for a few minutes. But next, I'd like to introduce Brandon Hoff, who is going to cover Fibre Channel, or securing data in the data center, which is somewhere that we've traditionally not really thought of apart from physical security. Brandon, over to you.
All right, thanks a bunch. Yeah, so today I'll be talking about, in some way we've been talking about for quite some time is Fibre Channel security or security in the data center. The protocol used for Fibre Channel is called FCSP, Fibre Channel Security Protocol. We got version 2. Version 1 came out, I think, in 2003. Version 2, I think, was 2012. It provides the same things that IPsec provides for Ethernet. So we do, authorization, we do authentication, encryption. You can do, same thing where you can authenticate using DHChap or the other type of key exchange methods, or you can do encryption for confidentiality and privacy. It's got a lot of the same stuff. There's a full webcast, the FCI webinar that's there's a link in the PDF that come out that I go through actually how most or all of this works in more detail. But yeah, this is, why FCSP. It's really encryption for Fibre Channel. And we stole from the best, if you will. We leverage the ESP header that IPsec uses, and so we rebuild the Fibre Channel frame. We add the front, the ESP as defined in RFC 4303, and then we also have some optional headers and other items that we can use in terms of other types of communications of Fibre Channel. One is CT authentication, and that's it's a common transport. It's a way that management commands can go through a Fibre Channel network, and that can be encrypted the same way. So it's very similar. We need to get pre-shared key, which is the next piece. Is Fibre Channel offers you 5 options today. The initial required was DHChap with a null option in terms of negotiating the keys, and then IPv2 authentication and the session keys are all created based on a shared secret. There's other ways to do this, and all the way from certificates to passwords to the same thing that used for IPv2 authentication, which is standard with IPsec, VPNs and stuff that use usernames and passwords. So all these create your ASP header as well as your CT authentication packets, and this is how you build up, all the passwords and secrets inside Fibre Channel. In terms of key management, so what this means is you got to go through and you need to be able to populate keys everywhere. And so we have secrets, passwords, and certs are different things that people can use for authentication. And the initial standard was leveraging radiuses of servers that different devices can communicate with to authenticate the secrets and authenticate credentials as they logged into the network. We use mutual authentication, so each device needs to authenticate to the other. A lot of devices today actually have SP authentication implemented, although I haven't seen it deployed in the real world anywhere. So at end user sites, I haven't seen SCSP authentication actually actually installed or deployed, but that is something that's offered. One challenge here is that once you start getting lots of secrets, you basically have your name, a secret, which is your worldwide name, and then some kind of cert or something behind it, password, secret, whatever you like to call it. And then if you have lots of these in the data center, if you have 50,000 or more credentials, it becomes an N-squared problem to manage, so it becomes quite difficult and hard to manage inside the data center. Options for managing credentials are Radius, KMIP, Public Certificate Authority, or Internal Certificate Authority are all available. But unfortunately, right now, these aren't supported on any open systems operating system today. But the standards are there, and they can be implemented as people demand them to be implemented. Which actually brings me to the second part of my presentation, is really, okay, when people ask me about encryption for Fibre Channel, what they're really asking is, okay, what are the issues here? What are the things I want to protect against? What should my Fibre Channel security look like? And one of the things benefit of Fibre Channel is an air-gapped network, and it lives inside the data center for the most part. And so it's in a secure perimeter. It's inside the data center, and you just need to look at all the different points around it to figure out what to secure. I've got outside jobs. Outside jobs are when you come over the Ethernet network. It comes up from the outside world. It's probably more prevalent when people are trying to hack into servers. How do I make sure my server, my operating system, my drivers, all those things are correctly installed and secure? So we'll talk about that. Inside threats. So these are people who have access to some sort of the infrastructure, maybe inside the company, maybe not type of inside the data center, but still have access to the networks and stuff. And those guys tend to be a little more dangerous because they know where the data is and they know what they want to steal, but they don't tend to be too prevalent. And then there's unlikely threats. And unlikely threats are really, if you get access to a data center, you're probably not going to pull in a analyzer and look at, try to steal data off the wire. You're probably going to pick up a bunch of disks and walk out the door with them. So that's kind of a good way to look at it and prioritize. In terms of, the full Fibre Channel storage security stack, here's a good list of things to go through. Digitally signed drivers, and this is something that all of us hardware providers provide, where we integrate with the OS systems and their tools and OS security guidelines to sign the driver, so that when you install a driver, the OS can check it and validate it's a valid driver. Other one is secure boot. So UEFI has secure boot now, and we can do UEFI Fibre Channel boot. And that way, if you're booting from SAN, you can boot from the right thing, the right area you're booting the right OS. You're not booting a malicious OS or an unintended OS. So secure boot's important. Third one is firmware upgrades. So I do on all my adapters have actually ARM processors, a bunch of ARM processors running on there. We want to make sure the firmware is the correct firmware. So we do digitally signed firmware updates and upgrades. So we check the firmware, check it against either software key or hardware key that's stored on the device itself to validate that the firmware is correct. And then as some of the other presenters talked about, securing all the user interfaces. So securing management access to the servers. We all know do that. Protecting and the management interfaces for the directors and the Fibre Channel switches across the network. That's very important. So authentication, all your standard stuff there, user ACLs, RBAC, SSL, TLS, all the things that we talked about before. And of course, controlling the management interface and storage system. That way people can't log in the storage system and pull data out of it. And then you have Fibre-based authentication authorization. FCSP is authentication, but what most people use are zoning, which provides access controls, which is more of an authorization. It's not authentication. I also have LUN masking, so the storage system itself can actually give you access control based on your role or who you are as a server, what operating system you are in terms of what you have access to. And those are really commonly deployed for, and it can be LUN masking and or namespace masking if you're using NVIDIA or Fibre channel. And then, of course, in the storage system, having digitally signed software stacks is very beneficial. Kind of what I talked about before. That way, malicious tools and malicious code can't get, injected into the storage systems. For encryption, so here's this. I think we talked about that a little bit. Very similar to what the other speakers talked about. Basically, encrypt data rest. That totally makes sense. Data in flight, encrypted across between data centers, because that's where you're going to see issues and errors. If you're going to use Fibre channel over IP or FCIP, then you can use IPSec to encrypt it across IP networks. If you're going to use dark fiber and run native Fibre channel, you can use FCSP for encryption. The key management is pretty similar, pretty easy because usually you're using a single vendor and not very many links. So it's a good solution for encryption for Fibre channel when the data moves outside the secure perimeter of the data center. And then for the rest of it, focus on minimizing costs and risk. So, security can get expensive, complex, and hard very quickly. Don't do the things that you don't have to do, like, just as the other presenter talked about. People really don't encrypt data inside the data center. And with that, I'd like to turn back to Alex.
Thank you, Brandon. We had a really good question in the question section that says, what type of network security is the baby in the background using? Well, I can answer that one. It's TAP, T-A-P, Pay Attention Protocol. I remember my two kids used to deploy it quite frequently. Anyway, in summary, what we discussed today, we discussed storage network security framework, the areas that are vulnerable to attack and how we might go about, in general, a high-level overview in protecting them. We talked about data in motion security. We talked about private and public cloud and how we secure that. We talked about securing data in the data center. And these are all aspects of ensuring that data in transit is secure. And I think the thing that we can show quite safely and quite soundly is that we do have mechanisms, and good ones in place, for making sure that we can secure your important data. It requires more than just putting the stuff in a tin, putting it under lock and key. It needs in-transit security. So the whole goal of this presentation today was to give you an overview about securing data, about making sure that that data is secure, whether it's eavesdropped, whether it's intercepted, copied, hacked, whether it's on a public or a private network. And as a couple of the speakers have said today, ensuring that we are moving into an era where more and more of our data is on the edge, and it's increasingly insecure and unreliable, and that actually demands that we think of security as a first part of any process when we're looking at data in motion. It's not something that we add on afterwards. It should be a part of our thinking right from the beginning when we're implementing systems. So, the resources that we have available, and we're going to add another link to this, the one I put up in the audience display area earlier about SNIA and TLS. We'll add that link to this as well. But there's a set of on-demand educational library pieces that cover more than just this. We talk about storage and security, protecting data at rest, which is something we hinted at today. There's an encryption 101, a key management 101. There's a range of presentations that SNIA provide to educate you on this important topic. You can follow us on Twitter, on SNIA NSF, for those of you that are Twitter fans. And we've got other presentations that we're planning to do in the very near future about protocol security, which is a level above the security we were talking about today, and about hardening, how we go about hardening systems to make sure that they're secure and robust. So, rate this webcast as you leave. That would be very valuable. And I would like to think that we have tried today, against all the odds, by the way, we have had a few issues, I must admit, but we've tried to give you some valuable information that you can take away and think about and consume. Remember that we've got an educational library that covers a whole bunch of educational topics, and any questions we didn't get around to answering, the one or two, we will put them up on the blog. That's SNIA-NSFblog.org. In the meanwhile, I would like to thank my guests today. I'd like to thank Claudio DeSanti from Dell, Ariel from NVIDIA, Cesar Obediente from Cisco, and Brandon Hoff from Broadcom for presenting on this interesting topic. Thank you very much indeed. Take care and have a good day wherever you are and whatever you're doing.